Well, another example to get some facility in dealing with these kinds of things. Uh, this one is an example problem. Show that if these ANs form an orthonormal basis, in other words, an orthonormal basis really entails a couple of things. One is that they are orthonormal, and that's this condition. And also, this summation, this is really a completeness relation so that you can expand any vector that you want in terms of this orthonormal basis. And that's really what's entailed in this basis set, is that you can expand any vector in it. And that one way to express that very succinctly is with this operation. Sum over this the outer product of the basis set with itself, and summed over n is just the identity operation. Well, show that if you had one of these anyway, then a unitary transformation also forms a basis where U is a unitary operator. So it transforms an orthonormal basis that's complete into an orthonormal basis that is complete. This unitary transformation does. And of course, unitary is U dagger, and so U dagger is the inverse of U. So the Hermitian adjoint of the operator of a unitary operator is just the operator's inverse. So pretty much like we've done earlier, we do this transformation, this operator onto the basis elements, basis set, and that'll transform into a new set over here. And we need to discover some things about that. Now I can take the adjoint of this, and that's just the ket becomes the bra, and these go in reverse order, but you pick up a U dagger, which for you, it's unitary, so I could put U or U dagger there, whichever one you want, I suppose. A U dagger or U inverse, whichever one that you want. And now then I take the scalar product between these two, one with an M and one with an N. So UN, and call this one the nth one, and UM. And I get this in terms of UN, and then this for M is just U operating with AM. But these two are inverses of one another, so I get the identity element. And then I know these are an orthonormal basis, and so the inner product is it preserves the orthogonality, the orthonormality. So the unitary transformation and change of basis is pretty powerful in that it changes one orthonormal basis set into another orthonormal basis set. So the orthonormal, that doesn't really get completeness, but we can show that in a similar fashion. So I look at this relationship to find out if in fact it becomes the identity. And there I again just get for phi, it's just U on the ANs, and then phi n, well, we have that up above. The phi n's is a U dagger, like so. I can pull the summation is over n here, summation over n. U and U dagger don't depend on n, so I pull them to either side, U and U dagger. But I'm given that the ANs were complete, and so this is the identity. So then I get U dagger, which is U inverse, and that's just 1. So if the AN states are a complete orthonormal basis, then so is the transform of it, the unitary transform on it to get the phi n will be exactly the same. So it transforms a basic orthonormal basis into transforms a complete orthonormal basis into a complete orthonormal basis. Yeah. So again, very powerful. These unitary transformations are in this regard.